morning, students. It's Friday. Woo! It is 5/22/20, and today we're going to start a new unit. We're going to talk about water, and first of all, we're going to talk about the fresh kind of water, as opposed to the salty kind. So, here's for today. I can discuss the distribution of fresh water on Earth. In other words, I want you to know kind of, like, where is the fresh water on Earth? And then I can explain ways to purify water. That's most of what we'll get into. So, where is Earth's water? I want you, I'm going to skip past that one. I want you to imagine that this is a picture of a water tank, and imagine that this tank represented all of the water on Earth. And I want you to think about how much of that water is fresh water, and that means not salty, and how much of it is saline water or salty water. Think about it. Where would you put your lines? So, turns out that I have a wrong number. That's what it turns out. My apologies on that. It turns out 97.5%, roughly, these are rough numbers, 97.5% of all of the water on Earth is salty. Now, you really can't drink that. I have to explain. You can drink it. It's not like it's poisonous, but your body absolutely needs fresh water. So for any little bit of salt water that you were to swallow, you need a bunch of fresh water to allow your body to get rid of that salt. So you cannot survive on salt water. Okay? It's not toxic in small doses, but if that's all that you have, and maybe you remember our speaker who was on the USS Indianapolis that was here a couple of years ago, and talking about the soldiers that were, floating in the water there for, I don't remember how long it was, and after a few days they're getting delirious and they're convinced that they can drink this water because they're dying of thirst surrounded by water. But drinking that water just makes the situation even worse. And he didn't get into details, but he said it was pretty horrible. So we can't survive on this. We need fresh water. Only 2.5% of the Earth's water is fresh water. Now, let's imagine that fresh water. Let's just focus in on that fresh water. So let's focus in, let's focus in, let's focus in. There's all the fresh water on Earth. That's that 2.5% of water on Earth that's fresh. Where is that? Well, approximately 69% of that water is frozen in glaciers and ice caps. Now, by and large, that's pretty clean water. The problem is, nobody lives there. Okay? Nobody lives in central Greenland. Nobody lives, there's one research station, but it's very few people live in Antarctica. Okay? So, of all that water that's frozen up in ice, it's not located where people are and where we need the fresh water. And I have students every year that says, well, why don't we just drag it down? I don't know where I have it at right now, but at one point I did some research on how much water the city of Los Angeles uses per day. And then I kind of calculated that out. And I couldn't find where I put the math on that, if I still have it. But I think it was just the city of Los Angeles would need multiple super tankers full of water every day to haul ice for thousands of miles to get to our big cities is not a practical solution. It doesn't really work. So while that's where most of our, or the largest portion of our fresh water, okay, so all we're left with is this. About 30% of our fresh water is in the ground. Okay, and that's by and large some relatively clean water. And we use that. The problem is, it's taken a long, long time in the history of the earth for that water to build up in the ground. And in many, many, many places on earth, we are pumping it out of the ground far faster than it's going back in. And it doesn't take too much intuition to see that eventually that's going to be a problem. And we have places in the earth where the water tables are just keeping going down. Places where, like, you know, we're really fortunate here in central Wisconsin, in Edgar, in and around Edgar. I think my well is 160 feet deep. We hit water at about, I think about 80 feet, but you know, we have extra reservoir. A deep well around here might be 300 feet. Don't quote me on that. You know, there's places in this country where they used to drill a well that was 200 to 300 feet. Now they might be drilling 1,000 feet. And those wells, there was a program on PBS just recently talking about water and groundwater, and this was, I think, dealing with ranchers out west, and they said the cost of that well was going to be, I think it was around $500,000 to drill that well. Now, if they're drilling down deeper than the guy, you know, down the road who's got his well, now he might have to come back and drill a deeper well too, because his well no longer supplies the water. We're really getting to a point where we're having some struggles. So while there's a lot of clean water in the ground, some of it's not easy to get at, and not everybody in the world has access to that. So what's left? You see this little bit? Let's see, 69 plus 30 would be 99% of our water. So we have 1% of the water, of the fresh water, is everything else. Now, think about that. That means that every lake, river, stream, swamp, the water that's inside of plants, the water that's inside of animals, the water that's in our atmosphere, and more, only makes up 1% of all the fresh water on Earth. And the fresh water on Earth only made up 2.5% of all the water on Earth. So remember that tank? If this is all the water on Earth, that's the fresh surface water. That tiny little bit. 1% of the 2.5%. You know, and when you look at something like Lake Superior or Lake Michigan and they look huge, those are included in that. It's really a fraction of the water. So it may seem like, well, we still got a lot of water. Here's the problem. Actually, quite a lot of that is polluted. We have done some improvements. 50 years ago, my father-in-law grew up in Wausau. And he said as a kid, you go fishing in the Wisconsin River, and there's raw sewage floating in the river. He said you go fishing, and you reel in your line, you got toilet paper hanging on your line. There's a turd floating by. Yeah. Would you want to eat the fish out of that river? Yeah. Today, the Wisconsin River has cleaned up a lot. So we have, in this country, made, I think, some good headway in the last 50 years about, keeping our rivers and streams and stuff cleaner. But we still have problems in this country, and many parts of the world are having terrible problems with that. So a lot of that water is polluted. All right, so I guess what I'm saying is most of the water on Earth is not suitable for human consumption without some sort of purification. And here's a definition. Saline, if I use the word saline, that means salty. So ocean water is saline water. Okay? And there's saline water that's not just in the ocean. In Utah, we have Great Salt Lake. That's saline water. And in fact, Great Salt Lake is quite a bit more salty than the ocean is. So I wondered about how to do this with you, but instead I'm going to share from a past class. What I asked the class is just to try to brainstorm a list of anywhere you could get some water. And so here's the list that they came up with. It's a little bit sad to me that the first thing they went with was pee or urine. Okay, Mississippi River. Cacti. Cactuses, cacti. Okay. Some chicken noodle soup. A pile of snow. Lake Geneva. Tears. Coconuts. Rainwater. Well water. Green Bay. Green Bay is not just a city, it's actually the body of water. You know, if you look at Wisconsin and it's got Door County as kind of that thumb, Green Bay is that body of water in between the thumb and the hand. Water vapor from the Amazon, lunar ice, Plutonian ice, cow's milk, the Mid-Atlantic Ridge. All right, so I guess then of this, the question to you would be, which of those would you drink? I might take some water from a cactus, maybe from the chicken noodle soup. The snow pile is really, really hesitant, because remember, when you push up that snow pile, you're also pushing up whatever else was out there. You know, how many dogs, cats, rats, mice, birds did their business all over. You know, definitely stay away from the yellow snow. It's not all lemon. Coconut, yeah, I'd probably be okay with that. Tears are pretty salty, so I bet as a source of drinking water, that's probably not so good. Rainwater might be pretty good. Water vapor from the Amazon, yeah, I got to get it out of the water vapor form. I don't have access to lunar ice. Mid-Atlantic Ridge is a long ways away. Cow's milk, I'll go with that. Plutonian ice, if I don't have access to lunar ice, I certainly don't have access to ice from Pluto. Water from Green Bay, not without treatment. Water from Lake Geneva, not without treatment. Water from my well, yeah, I drink water from my well all the time. So there's a few of these that I'd be willing to drink, but what about those other ones? Let's go back to the pee and urine. Think about it. If you've got a sample. Now, if I were to remove everything that's not water, what I'd be left with is water. Can we do that? Can we do that? Can we remove everything else so that now we just have water, which is perfectly drinkable? And the answer is yes, we can. Sometimes it's pretty energy intensive. What are the contaminants that could be in those things? Okay, and so the contaminants come in three basic varieties. You got particles. Okay, so if your water is muddy, you could just let it settle a while, and the particles that are suspended in the water could fall out. You could clean up the water. Of more concern to me would be biologicals. That means bacteria, parasites, amoebas, viruses. Okay, and those are very difficult to clean out. They tend to be really small, smaller than a lot of those other particles. You know, muddy water, if you just let stand, will settle, but the biologicals largely won't. Okay, and then we have chemicals. If there's chemical toxins in your water, those are very difficult to get out. Okay, so these are different types of contamination. So here's what, you know, my rainwater, I think would have very little of any of those. My Mississippi River probably has all of those to some extent. Okay, that snow pile, who knows? It could have all of those. My well water, I feel pretty good about the particulates. You know, we should test our wells once in a while for the chemicals and biologicals. If a well gets contaminated, it could be very bad. The water vapor here would probably be very clean. I would certainly be, you know, Green Bay The water flowing into Green Bay is coming from a pretty industrial area, from the Fox Valley and Green Bay itself. I would be worried about chemical contaminants. I'd be worried about biologicals. We got to think about those things. How do we get rid of those? And how we handle each of these is a little different. Okay? So I'm going to go through with you two main ways of separating mixtures. And most of what we do is some form of one of these two or some combination of these two. So the first one's called filtration. This is a big vocabulary word. Okay? And you guys are familiar with filtering things. It's not new to you. You just maybe have never thought about what it means. To filter things means you're separating your substances based on the size of the particles. You know, imagine you're making a pot of coffee in the morning. You got a coffee filter in there. What's the purpose? The water, including the substances that it soaks and dissolves out of the coffee beans, the water goes through the filter, but the ground up beans, seeds really, stays in the filter. Why do they stay in the filter? Well, because they're too big to go through the little spaces between the paper fibers. The water and some of those chemicals soaked in the water will go through the paper fibers. The bigger pieces won't. Okay? Filtration separates based on size. So here we go. If I had a mixture that had all this stuff and I pour it through this screen, well, this screen's got big holes, so it only pulls out the biggest stuff. But then if there's another screen, you know, here this size gets caught, but all the smaller stuff goes through. Here's another screen, and those pieces get caught, but this stuff goes through. And here's a picture of a filter paper going into a funnel that we'd use in our lab. And that's going to filter out some really pretty small particles, and just the smallest stuff goes through. Filtration separates by size of particles. So get that in your head. Filtration has to do with size. Filtration, size of the particles. All right, so what if I got salt water? What if I had salt? What if I had a sample of water from the ocean and I want to get just the water out because it's salty? If I drink salt water, it's not healthy. I need fresh water. And if I put salt water through this filter,